Welcome back. When we last left off, we had we'd had the USB input connector, the charge controller, and the connector for the battery. And we connected all of the main wires except for the connection to the visible LED, and that's just because at the end, we're gonna have a few LEDs on the other side, and we're gonna put them wherever we need them. One thing, looking at this, that's bothering me a little bit is this is going to be fine. This is going to be fine, but there's no reason for this ground and this V-bus to be so close. So one of the things you can do is if after you've made wire connections, if you decide there's something that's a little bit off, that you just, if there's no reason for two wires to be really close to each other, you can always just click and drag and just kind of move them a little bit. Our grid is set a little coarse right now, so it kind of does sort of an ugly adjustment there, but that's fine. That's something that's nice to do. Sometimes after you get your power lines all run, it's just good to maybe just, nudge them a little bit here and there to get them a little bit cleaner. Let's go back to our circuit. And so I've got USB connector to battery charger to battery. On the battery side of things, I want to have a boost converter. So to do that, I'm going to use the boost converter part is the Feeling Tech. So this is the data sheet for a boost converter, and we can scroll down to the example circuit. This is an example circuit. We're pretty much going to follow this example circuit. So let's give myself a little bit of space here. Let's go back to components. Boost regulator, and we're going to place this wherever it kind of makes sense. We can give ourselves a little space. Space is out, and then hit escape to cancel out of that. Okay, so one thing is we're going to be connecting the input here, VCC, to VBAT. So we can do that right now. And it is okay to have the wire cross this part like this. It's not great, and it can cause issues if the shape of this is a little strange. Dragging across can sometimes visually kind of throw things off, but I think it's going to be fine for right now. So let's go back and look at that data sheet. The input, they have capacitors. We'll add the capacitors later, but they've got capacitors here. Capacitors on the input and the output. It looks like they have a mirror image set of capacitors on the input and output, and that's because this boost converter, to work properly, it really wants a good decoupled input and output signal. It doesn't, when it's going to charge up this inductor, it doesn't want to see, or it doesn't want that sudden surge of current to cause a big change in voltage on either the input or the output. A big change in voltage as a result of the current change can lead to instability in the feedback network. So a couple of things we have, this overcurrent program resistor. So we'll just use the value they have there of 10K. We got to have a diode. We have to have this voltage divider feedback network to give a signal to the controller. And then, of course, we have the inductor here. So let's do that overcurrent resistor. Let's see what that was. It was a 10K resistor. So we can just, again, go to components, miscellaneous devices. That's 3. And we're just going to still make sure the 0603 is selected. Right click it, place it. Spacebar will rotate it. Drop it there. Okay, I think I might do the inductor now. So looking at this, right, we have an inductor going from the input voltage to the inductor pin, and again, internally, or not again, because I haven't said it in this video yet, but internally, this switching circuit can connect this pin to the ground. So essentially, it can connect this to ground, and what that does is it starts building up charge. It starts building up stored energy in the form of a strong magnetic field inside of that inductor. And then it can, rather than connect it to ground, it can disconnect it from ground, which then causes that stored current to flow to the output. So let's grab an inductor. I had a common one that we're using in the schematic library. And I think I'm just going to take this inductor signal and wrap it all the way around just like it does in the data sheet. So I hit escape. That's going to be just fine. So let's see what else we got. We got to get this diode here. So for the diode, I'm going to go to the vault. So I'm going to go to the Explorer tab in this version. So one diode that I really like is if you search for B360. I really like, no connection at all, not logged in. It seemed to let me get it anyway. So I like this B360A. It's a good diode, it's a good size. The pads for it are pretty nice. The pads for it, they're big, they get close enough to each other too that you can actually use a variety of different diode sizes in the same footprint. I've always sort of liked this as sort of a go-to, a versatile footprint that allows you to actually put a lot of different physical types of diodes on there. And it's got that big bar that tells you which side of the diode is which. So we're going to right-click that and go place. And pop that in there like that. Hit the escape key. Give ourselves some more space here. Let's do that. Let's do that. Well, we can connect to the ground here. Ground to ground. It's starting to get a little messy. If I was really trying to be clean, I wouldn't do it like this. I'd probably find a better way to do that ground. But I think that's going to be okay. So the feedback network, if we look at it, we have a 12K on the ground side, an 88K on the V out side, and then that divided voltage goes to the feedback pin. In this example, we're doing 3.7 to 5, which is exactly what I want for my design. If, for instance, you were boosting from 3.7 to 10, I think keeping this as a 12K, you need something like a 180K resistor up here. You can do the calculation. It's somewhere in this data sheet, but yeah, right here. So here's the calculation for how to get those resistor values. But we're just going to follow the example exactly. So an 88K at 12K. Okay. So this resistor right now doesn't have a name. So one thing I can do is if I just press the shift key and grab this, it's going to grab a copy of this. Again, hold the shift key, grab it and hit the space bar to rotate it. And put it around there. This one was This one was the 88K. So I'm kind of flipping it for my design here. Maybe this one was 12K. So let's just go back. So in this case, I have the ground side of the divider up top, and the side that connects to the output voltage is on the bottom. But yeah, the one touching the output voltage was 8.88K, the one touching ground is 12K. The one touching ground is 12, the one touching the diode is 88. But again, when I held shift and clicked the part and dragged it, that made a copy. And I usually only do that when it's non-annotated, because if it is annotated, it tries to automatically increment the part, and that even if the number already exists, it's not very smart about it. So, okay, what else do we need? We need some capacitors on the input and output of this. So one of the things I do is we have a parts library in our program. So in the dry cabinet, we have a bunch of parts. And this Excel spreadsheet tells you basically the list of all the parts that we've got. You can find this on the R drive in the R drive/SMD components library. And I see for the tantalum capacitors that we've got, in my case, my output is only 5 volts. So these are only good up to 10 volts. So they'll fail if you apply more than 10 volts to them. But I got a 22 microfarad capacitor that's good to 10 volts. Now, if you're doing a 10 volt design, I would not recommend using this because the 10 volt size is, you know, if you're actually applying 10 volts to a 10 volt rated capacitor, you're going to blow the capacitor. You always want to have a little bit of buffer space. The 16 volt one would probably be okay if you were outputting 10 volts. But I'm only outputting 5, so the 10 volt limit's going to be just fine. One thing I'll notice though is the package here is 1210. So if I'm trying to find an equivalent part to this in the Altium library, I can just go back to Altium, go to Explorer, and type in 1210 tantalum. I keep saying that. So I can log in here because I have an account. So that's going to stop me getting the message. If you get that message and you don't have an Altium account, you might just kind of be in trouble. So. Okay, so these are all tantalum capacitors that have the same footprint. Now, one thing I want to show you is sometimes you click a part and you'll see associated with that part you have a schematic symbol and then a bunch of board symbols. So let's just look at this one right here. Well, let's do a 20. Let's at least do one that's labeled 22 if we can. Yeah, so this one's labeled 22. So the footprint is 1210, which is what we need, but it's got 3 different footprints. And if you look, when you click on these different footprints, the picture changes. So what these are is these are different densities of footprints. So when you're doing an actual board design, typically you can choose between high and low density components. And high density components would be components that have small footprints where the part barely fits on them and there's not a lot of extra copper. And that allows you to get the parts tighter. It allows you to get them closer together and fit more parts on the same side board. But for us, because we're doing these by hand and we want to be able to get a soldering iron in there, I'm almost always going to click around until I see the footprint that has the biggest amount of pad hanging out. So I'm probably going to do that and then place that component. And I'm going to grab 2 of them. So I'm going to put one on the input here, and I'm going to put one on the output here, and then hit escape. Now, to get my ceramic capacitor, I'm just going to do an 0603 because I also want a ceramic capacitor in parallel with this for high frequency response. So I'm just going to go to miscellaneous devices, and it's cap semi. And then I want to scroll down and make sure 0603 is selected. I click place, space bar. This is not a polarized capacitor, so I don't really care what orientation it's in. Now I'm going to connect up grounds to these. And I'm going to extend this wire out. And actually now, this is a good time. I should label this. This is my actual 5 volts output. So it's a good idea for me to name this output. Or if I know this is just going to be my main system voltage, this is going to be my main voltage that powers everything in my system, which is the case here, then instead of just writing a name for this, I might as well just use a symbol. So if I put this tag here, what I'm doing is I'm not saying, you know, drive this signal with this VCC voltage. All these tags, all the ground tags are, all the VCC tags, these are just labels. They're just fancy labels. So what I'm saying is this signal of my design is labeled VCC, and anywhere else in my circuit where I put a VCC, I want that electrically connected to the signal right here. Okay, so I think this is pretty good what we got here, but there's another thing I want to point out, and that is we have a battery and a battery charger, and it's feeding directly into this boost converter. Is there any way to turn this off? So there's an enable pin on this boost converter. The problem with enable pins on boost converters is if you disable a boost converter, the only thing you're doing is stopping it from switching. It's still, if you look, right, you still have a direct path through an inductor to your output. So you can stop this from boosting, but if your battery is powered at 3.7 volts, you're still going to have about 3.7, well, probably something like 3.4 because you're losing some voltage across the Schottky diode. But you're still going to have current flowing out of the battery. So basically, when you're using a boost converter, disabling the boost converter does not stop the flow of current out of the battery to your circuit. If you do want to have a switch that turns off your circuit, you have to basically put one in place. So if we want to actually be able to disconnect the battery from the circuit and totally turn the circuit off and not discharge the battery, we need a switch here. The problem is it's possible for this, I mean, this circuit can draw a lot of current. We might be drawing up to an amp from the battery from this circuit. And so if we want to buy a switch that can handle that much current, it's going to cost us a lot of money. The alternative is we can put a transistor in here and have a switch that turns the transistor on and off. And then that way we can have a low current switch that's cheap, that's turning on and off a transistor, saves us money on hardware, pay a little bit more with the electronics, but it's usually worth it. So let's just do that right now while we're doing this. So if I want to put a switch in here, I'm going to break this. I just clicked on it and pushed delete. I'm going to have to redraw that. It just cut the entire net here. But what I can do is I can get, if I go back to my components, I can do a PMOS. Remember, we always want a PMOS switching on the high side up here. So I can put a PMOS transistor here, and it's very important to get the PMOS transistor in the right orientation. You don't want the collector emitter to be the wrong way. And the way I always tell is by the body diode. So basically, I want this transistor to block the flow of current from this side to this side until I apply a low voltage to this gate. And you can see the way the body diode is faced, there's no way for current from here to here to flow through the body diode. All right, it's going to get blocked by that diode orientation. If this had been flipped around, current can easily flow in this direction through this transistor. So basically, if we're trying to use this transistor to block current, we want to make sure the direction current needs to flow is opposite the direction of the body diode. So this orientation is correct right now. So we will connect up just to get this in place. We'll connect this transistor here. One thing about Altium is you don't have to, if a wire overlaps an endpoint, it counts it as connecting. You don't have to just click each one. That's a blessing and a curse though, because sometimes if you're sloppy with your schematic, you can accidentally have connections that you do not intend. Okay, so now we need a switch that's basically going to turn this on or off. So what would make this turn on? Well, With a PMOS, conduction happens when the voltage at the gate is more than 0.7-ish volts from the voltage at the collector. One thing I would probably do is, or at the emitter, probably let's tie a resistor here to here and then have the switch just pull it down to ground. So let's put a big old resistor that keeps this transistor turned off, and then we'll put a switch in here that if the switch is switched in one direction, it'll actually ground this gate, which will pull this transistor down. So I've got a whole bunch of these unmarked resistors here, so I'm just going to hold shift, click this and drag it, put this here, and I will wire this. Okay, so now, for right now, basically, as wired right now, this entire transistor just functions as a diode that blocks current from flowing this direction. Because this gate voltage is always going to be the same as the voltage here, which means this is never going to be conducting. So it's just a diode blocking current flow. I want this, in real life, I want this to be bigger than 12, so I'll just say like 100K. Now let's put a switch here that we want a switch that allows us to switch it so that this connects to ground, which will turn this on. So let's go to slide switch, right click, place. Okay. So what we're going to do is we're going to ground one side of this. Okay, so now what's happening here? So when the switch basically, when it switches back and forth, it connects one side of these terminals to the common or the other. So basically what's going to happen with the switch is when the switch is in one direction, this common pin is going to be tied to ground. That's going to turn this transistor on. When the switch is in the other position, this common is going to be tied to this floating wire here. If this wire is floating connected here, then it's just a wire just dangling off the end of this gate. This gate is still tied over here, which means this gate will never have 0.3 volts lower voltage than here, 0.7 volts lower voltage than here, which means this transistor will never turn on. So basically in one direction it turns on a PMOS, in the other direction it leaves it off. So this should work just fine. I think this is pretty much enough for now. So let's look at, we've built this circuit. We've actually done a lot of work in between messing with the board. So let's take the circuit we got and let's do, let's first annotate it. Now let's do design update PCB document. It's in all greens, which means it was able to do all the changes that were requested. So we're going to zoom out. I'm holding shift and I'm doing the scroll wheel. Now I'm right clicking the pan, shift scroll wheel, control scroll wheel. So Altium drops your parts outside of your active board area. So sometimes I just grab them and just get them close, just so I don't have to keep going all the way over there. Okay, so again, I kind of want to, sometimes I can't really tell what's what here, so I usually go right back to my schematic and I say, what's the first thing I encounter? First thing I encounter is R5, switch 1, and Q1. So let's go back. Let's do R5, switch, Q1. So let's get this switch set up in place. Okay, so what's my thought process here? I don't really have a thought process right now. I know that VBAT is here, net Q1 now. We should probably rotate it like this. Okay. So now we can get VBAT here. We can gate this thing with net Q1. Yeah, I'm pretty happy with this. So I'm pretty happy. Let's not route this thing yet. We'll just know that everything is pretty much oriented. The ground is the only thing that's over here, but we can get a ground signal over there. This is just the gate signal. It doesn't need to be a huge connection or anything. Okay, so let's leave that there for now. So let's go back and see what our next things are. So next we got C1 and C2. I always like to put the high frequency capacitor closer to my next stage of my circuit than further away. Now we've got R8 and RIC. Let's just see the IC over here. So R8 is this little, it's up here. So if we actually want to do this part the way it's laid out, we gotta rotate it by hitting the space bar. That looks like it's probably what we actually want to do. I'm a little worried that I'm not seeing this connected anymore. Oh, lo and behold, that's because we had deleted this connection here. So little mistakes can kill you. Okay, now they're connected. So, and that R8 is here-ish. So. I might keep it a little compact here. I don't know if it's necessary or not yet, but might as well if we can. And I don't worry too much about these annotations, but if it's irritating me, I'll rotate them. Okay, that looks like that'll be good. Let's get the inductor and the diode in there. So one side of the inductor touches the input voltage, and that's this side over here. And the other side of the inductor is the diode. And then on the output we got the caps. Okay. Now all we have left is that dang resistor feedback network. So there's just no good way with these ones sometimes. So we got to get the middle signal here. So VCC's over here. The problem is this net D1 has to get to this pin. There's no real good way to do this. So this is a high current pin. The ground is, this is a high current pin. We could probably route it through the bottom. So we can eventually route this one through the bottom. I think that's going to work okay. So if we route that through the bottom, we just want to not block our ground here. So okay, this R6 has a 2 on it, and that's bothering me. Oh, look what I did. this resistor here, this is a good lesson. It wasn't actually touching the end of the pin. See down at the bottom of this resistor down here? It looked like it was because it was touching this, but the actual bottom of the pin is right here. And I had it just set right at this little knuckle of the drawing. So I gotta do that. Yeah, that's a big deal. And that's partially why you double check yourself. It's also partially why you don't do this stuff at 2 a.m. Update PCB document. Some nets are not able to be matched. Yeah, this happens. Okay, now it looks like it's connected okay. So, I think it figured itself out here a little bit. I'm just going to do this. Okay, now I'm tempted to route this section here. It's like I can move this okay. Move this okay. So I'm actually going to route this, and the reason I'm going to route it is because we have some pretty critical routing, and while I'm still thinking about this, I might as well get this routing done. So let's do some high current routing. So we'll start with the connection to, well, first of all, I can make this a little more compact here. I don't want to get too compact because I don't want to have stuff too close to this battery connector, but I at least can do that. So let's start running the power here. Okay, it's still probably thick enough for this power application. Actually, I'm going to undo that. That signal didn't need to be quite that big, so for now I'm just going to save it. This signal does need to be big. This is all the current flowing through that switch. So this one is going to be fairly beefy. That's probably good enough. I'm just going to run it all the way through to here. Okay, that's a little sloppy. You might be tempted with this to. I'm just not happy. I'm just going to delete this. Just hitting the delete key. Try not to hit pads. Okay. I'm just going to run this wire all the way across here. Oh, escape. Looks good. That looks a lot better. All right, let's keep going with this power line. So, yeah, power feeding into our inductor. The other side of the inductor flows to the diode. Diode goes to the leg bone. This is not a high power connection, but it's fine. Let's do some grounds here. So I always love connections at especially battery plugins, but anytime I have a connection in a through hole, that's a nice high current location there. So I'm going to keep this ground running on the outside. I kind of like this notion of just my ground running along the bottom rail. Come back for that one. Let's get the ground in here. Ground connection there. And if we remember, this diode connection, or this inductor connection, something's got to snake through here. So I'm going to do that. And just so this size trace is really good. I'm going to hit the tab key and check what size it is. Not yet. I'm going to hit the tab key. While I'm actually routing. So what size is that? Hit the tab key. So that's 28 mil. 28 mil really seems like just a good choice here. So this is not a high current pin, but looks like it's going to work out just fine anyway. Let's connect these grounds up. Let's do this to ground here. Okay. Looks pretty good. So we still have this switch. I'm not too worried about it. And the main reason I'm not too worried now is because this switch is for the edge of a board, so it's eventually going to have to be moved to the edge of the board. So we can still route a little bit more here. Okay. It's pretty good. It's pretty good. A couple of things still not routed. We'll get to them again. You know, we've been doing a fair amount of routing on this board, and one thing to notice is we haven't had to use the bottom side of this board at all yet, I mean, except for this guy, but this has all been on one layer, which is pretty good. Pretty fat connections, pretty good connection from left to right. Let's take a peek at what it looks like in 3D. So I'm going to hit the 3 key. Look at this board in 3-dimensional view. And sometimes this is good just to see when something's maybe a little scary. So this inductor probably doesn't have to be that close to the chip. So I'm going to hit the 2 key, go back to this, and you know what? I can move this a little bit. I'm going to just move that inductor just a scooch. And then I'm probably going to come back and clean up some of this stuff. I like that better. Just give it a little more space. Okay, you know what? Let's have some fun. Let's cap this video off by doing the board outline. So we've got all this stuff together. It's starting to shape up fairly nicely, but this project is for a Christmas tree that lights up. And so to make this light up Christmas tree, let's draw a Christmas tree board outline in Altium. So drawing board outlines in Altium, especially if you're going to get creative, there's a million ways to do it. And one thing to note is if you need an advanced board design, Altium allows you to create a board design out of like a 3D object. So you can take a 3D object, you can take a service from a 3D object and generate a board outline from it. Altium is really good at that. What Altium's not good at is sort of intermediate drawing skills. So like being able to just do drawings with things like splines and NURBS and all those other nifty little drawing tools that are fairly common in line drawing programs. You can't do that. Altium's really, its control functionality is mostly meant for manipulating conductors and components. So you gotta kind of trick it to be able to do drawings. And one of the ways I trick it is I like to do all of my drawings for my board outline in a metal layer. Because the top and bottom metal layer, or the middle, all the metal layers basically, Altium gives you, for some strange reason, you get easier control over the shape of curves and things like that if you're actually treating them as wires and routing them versus if you're just treating them like lines that you're creating with any old layer color. So to show you what I mean, what I'm going to do is I'm going to go off to some side of the board over here, and I am going to just start drawing a picture. And I'm going to draw that picture. First thing I'm going to do is set my grid very coarse. So I'm going to hit the G key, and I'm going to set my grid to something like 100 mil. Yeah, that should be good. what, maybe I want my grid to be, so I hit the G key to do the grid. Maybe I want it to be 200 mil. Because I'm not a very good drawer, so I'd rather have this thing be unnecessarily big than make my life miserable later on. Okay, so first of all, I need to know what general size I have to work with. So most fabs, to keep things relatively cheap, you're going to want to keep things sort of within a 4-inch by 4-inch box. Technically, it's a 100 mil by 100 mil box, or sorry, a 100 millimeter by 100 millimeter box. If we really want to get a 100 millimeter by 100 millimeter box, so right now, if you look at our units, they're in mils. If we hit the Q key, and then move our mouse, now we're in millimeters. So hitting the Q key switches our units. So we can hit the Q key, and then we can hit the grid, and then we can go to grid properties, and we can do something like 5 millimeters. And then let's just make a box. I'm going to choose a mechanical layer that nobody ever uses. Mechanical 12. And I'm just going to make a line. And I'm going to just make with mechanical 12 a box that's just 100 millimeters by 100 millimeters. So start down here, and what I'm doing is I'm looking at that top left corner. You see my delta X? My delta X is 45, 50, 55, 65, 70. I'm going to take this all the way till it gets to 100, and boom. Double click that. Kind of go all the way up till it gets up to delta Y of 100. Double click that. Now we're going to do a delta X of negative 100. And then we're going to finish it off. Okay. So I have just made a 100 millimeter by 100 millimeter box. So my entire, whatever shape I make, it really should fit inside of this box. And I'm going to make a Christmas tree. So let's fit it inside the box. I'm going to have the top of the Christmas tree fit this USB connector. So it looks like it's going to have to be at least 2 of these boxes wide. And then we'll see what we can do for the rest of the tree. So I'm going to stick with this layer size here. With this mechanical 12. I just picked a random mechanical layer. You'll see what I'm going to do with it later. But I'm going to start making a tree inside of this. So I'm going to do, start here, and I'm going to do, so one thing you'll notice is if I hold down the shift key and press space, it takes me through all the nifty different ways I can make shapes. And let's say I want it to curve in the other direction. I can, instead of hitting shift space, I can just hit space, and it's going to flip it over to the other side. So shift space gives me my general shape. Space flips it in the other direction to have it bend in the other direction. But one thing you'll notice is, let's say I go to this radius here. Okay, so I don't have a way right now to control easily the radius size here. There's hotkeys that Altium has for radius, and they just don't work, and that's because I'm drawing a line, I'm not actually routing. What if I try to route something? So if I try to route something, you'll notice it automatically switched me to this metal layer here, which is fine. So we can stick with this for now. I'm going to hit the tab key, and I'm going to change this to just something tiny like 6 mil. And now I'm going to just use this top metal layer to make the outline of my board. I'm going to just make it in the metal layer, and then I can always switch it later on. So if I want to have my tree be rounded, I'm going to hit shift space. Kind of like that. Now one thing is, now that I'm actually routing a wire, I can hit the comma key or the period key. And if you look down at the very bottom, you see that radius? And as I hit the comma key, the radius gets smaller. And as I hit the period key, the radius gets bigger. So this actually gives us a way to dynamically change the curvature of this as we're using it. And again, this is not available when we're drawing lines. It's only available when we're routing. I don't know why they do that. It seems dumb. So I'm going to get it close to 5 millimeters. It should be able to give me a decent tree here, I think. I don't know. Can I get a... Yeah, you're going to see how bad of a drawer I am now, so we'll give this a shot. How nice of a tree can John make? Things are looking good. I'll be honest, it's looking kind of tree-like here. Okay, let's bring it on home. Let's make a stump here. All trees have those. And then how many? I had one, two, okay, I had 1, 2, 3, 4, 5, 6 there. So 1, 2, 3, 4, 5, 6. Oh, okay. And then I was doing 3 and 2, back 1, 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 and then finish off. Now, one of the problems is I can't actually ever touch this last wire. So if you're routing a wire, you can't actually have it double back on itself, or Altium's just going to say, oh, well, you're just done routing. So sometimes what I'll do in a case like this is I will change my grid to something a little bit finer. And then I'll still have that radius, but I'm going to stop this just before these meet. I'm going to stop this just before they meet, and then hit escape. And now what I'm going to do is my tree right now is in a metal layer. I'm going to convert it. So one thing I know is I know my tree now fits inside of this big box. Let's delete the box. Okay, now I'm going to select this entire tree. And I am going to go to properties, and I'm going to switch this from top layer to that mechanical 12 that nobody ever uses. Okay, and now I'm going to go back to mechanical 12. And now I am going to draw a line to fill in this little gap here. Oops, one thing is this line had a weird thickness. I'm going to double click it and set the width back to 6 mil. Okay, perfect. So now we got it. Okay, so this is our Christmas tree shape. We know it is less than 100 millimeters by 100 millimeters. Now, how do we actually make the board out of this? Easy. Select the whole thing. We go design, board shape, define from selected objects. Boom. It's that simple. So what if we want to move our circuit into there? Select it. Move it on in. Now I probably want to go back to my original grid. Pretty good. I'm actually pretty happy with this. Okay, it's not bad. Now, let's switch. So first of all, we did all this hard work to make this. Let's get the payoff here. Let's hit the 3 key. Look at that. Beautiful. Makes it all worth it, doesn't it? You see that? 'Tis the season. Look at that. Christmas tree and everything. All right, I'm starting to get a little delirious. It's 2:40 a.m. here, so. All right, so I want this switch to be on the edge, sticking off the edge of this tree, so you can just kind of slide that little ornament back and forth to turn this on and off. So it's rotated weird, right? If I click this and I hit space, it's not going to work for me. It's not going to work at all. So how do I make this switch line up against the edge of the tree? Well, what I can do is I can double click it, or I can click it and hit tab. And I can go to rotation and I can start tweaking this. Let's try 205. It needs a little more. Let's try 209. Nope, 213. Oh, 213 could be it. Oh, look at that. 213 is at 214? No, 213. Potato, potato. I don't know. They're both kind of right on that line. But well, now let's check it. Now I get a better view here. Yeah, let's do 213.5. Okay, yeah, all right. 213.5. Apparently we can do that. That's learn something new every day. So this is good. So now we got this switch. If we hit 3, look at the 3D view. Look at that. So we got that switch hanging off the side of our tree. That's nice. That's going to be good. Okay. You know what? This is a great place to stop a video. And this is also a great place to save. So we're going to go right click, save. I think we can go save all, save everything, and we will call that good. We've got ourselves a tree, we've got most of our circuit, we're well on our way. Thanks for watching. Smash that like button and enjoy Christmas tree.